So silicates form, and they have to have SiO4. So this is what the silicate ions or elements, silicate minerals must have. They must have the silicone and oxygen. If they don't have silicone and oxygen, they are not a silicate. So they must contain Si and O, and they contain SiO4. So they have 4 oxygen and 1 silicone. And this actually is charged because if you balance it out, so it's SiO4 4 minus. How we get this 4 minus is silicone has a charge of +4. Oxygen has a charge of -2. So we have a +4 and -2, but we have 4 oxygens. So you would take 4 times the -2 equals a -8. So this came from the fact that we have 4 oxygens. So you have to times this number by 2. You have to times this 2 by 4 to get a -8. Then when you take 4 plus a -8, it equals a -4. So this is why the silicate has a -4 charge. So remember, the SiO4 is actually covalently bonded. So this is very strong because it's covalently bonded together. The fact that the silicate or the SiO4 has a charge allows it to ionically bond with other elements. Otherwise we would just have, if it didn't have a charge, it would just be silica. So most silicates have other elements like aluminum, potassium, calcium, and they're ionically bonded to the silicate structure due to the fact that it has a charge. So the SiO4, it actually makes what's known as a silicate tetrahedron. I'll write the word out first. Tetra meaning 4, hedron meaning shape. So silicate tetrahedron is a 4-sided shape. It's a pyramid which includes the bottom of the pyramid. So its general structure, you have the Si in the middle, and then the Si is surrounded by 4 oxygen. So if I were to connect these 4 up, the silica is in the middle, and that's in the back. So that's generally what it looks like. My silica is not too much in the middle, but it should be right in the center. So that's what you get is your silicate tetrahedron. And then these oxygens will bond together to link up the silicates, and you have your silica still in the middle. And so you start with an isolated silicate tetrahedron, and then they build on that by connecting up the oxygens. And you can actually connect up this oxygen as well into your silicate. You can connect up this one, you can connect up this one. So the structure gets more and more complex as you start connecting up your different oxygens. So if you look at this picture, here's a silicate tetrahedron with your oxygen and your silica in the center. So once again, this has a +4, these have a -2, so you end up with a total of a -4 charge. So the silicates are broken up into different groups depending on how the arrangement of the silica tetrahedron are, how many oxygens they're sharing. So the first one is independent tetrahedra. You might also see this as isolated tetrahedra. What that means is there's isolated tetrahedron. So they're floating around and then they're ionically bonding with other cations. So cations are positively charged. Anions are negatively charged. So the cation is your positive charge. The silicate tetrahedron is your anion because anions are negatively charged. So tetrahedron is your anion. The things like calcium, sodium, potassium, magnesium, and iron are your cations because they're positively charged, and you form an ionic bond between your tetrahedra and these cations. So here the next step is combining one oxygen or two oxygen per tetrahedra, and those create single chains. So this is the next grouping, is your single chains. So the tetrahedra, once again, are covalently bonded, and then they ionically bond with cations, which are shown here. The next is the double chain. So basically you're taking two single chains and combining them so they're sharing a third oxygen. So each one, here you can see that how they're forming. They're making one chain, so they're combining together to share oxygens. So once again, these will ionically bond with different cations. Every time you are combining and basically excluding an oxygen, that changes the charge of the anion, which is the silicate tetrahedra chain. In this case, this is the double chain. So it can bond with different elements. Then the next one is the sheet silicate, which basically you're taking double chains and combining them together and making sheets. So you can see here, and then these will combine with this one to make the second layer of the sheet, and they have ionic bonds between the sheets. Sheet silicates generally have one plane of cleavage because they are ionically bonding those sheets together, so they generally have one sheet of cleavage. Three-dimensional network, these are also called framework silicates. Framework silicates are extremely complicated. All the oxygens in the tetrahedra are bonded, and therefore they do still have a charge, but they are extremely hard. So these generally have a high hardness. Hardness is generally greater than 6. So quartz and the feldspars all are pretty hard and strong because they have a lot of covalent bonds and not as many ionic bonds.